this morning, we learned there's a whole bunch of different reactions that carboxylic acids undergo. There's like esterification, and they make it amides, and all sorts of different things. And so one of them is esterification in reverse, where we break ester bonds. And in this particular instance, it's called saponification, because we are releasing fatty acids, and that's different from your typical carboxylic acid. What's the difference between a carboxylic acid and a fatty acid? Can anyone remember what that was? He said to stunned silence. What makes a carboxylic acid fatty? Man, we were off to a flying stop this afternoon. It is the length. So if I make a long acid, this part is hydrophilic. It is soluble in water. And this long part over here, which is basically just all carbons and hydrogens, is not soluble in water. And so the usual sort of carboxylic acids we've been dealing with so far, we're dealing with acetic acid mostly. That's completely soluble in water, because it only has a single methyl group attached to the carboxylic acid part. So that means that it's really, really soluble in water. But the longer and longer and longer you make that carbon group, the less and less soluble it gets in water. And so basically anything that has greater than about 10 to 12 carbons in it is considered fatty. And one of the reasons is that really long carbon molecules, as we remember, have a lot of London dispersion force, and they stick together. So that's why, like at room temperature, long fatty carbon chains will stick together and make solids. There's a reason why butter is a solid at room temperature. It's because it has a lot of these long fatty acids in it that stick together, form a lot of these London dispersion force interactions, and becomes solid at room temperature. Once we start introducing double bonds in there, we break up, we force the long chains to take these breaks. They bend into a particular direction. And once they start bending, then they don't fit together quite as well. They have less London dispersion force. And then you start to get, instead of solids, you start to get liquids like vegetable oils and that sort of thing. There's a reason why margarine tends to melt, excuse me, at a lower temperature than butter does, because it has more of these double bonds in it. But I digress. So the reaction we're going to be doing today is called saponification, and that is breaking the ester bond. So what is the alcohol and what is the acid? I think we should, come on. And Susan is not being kind today. It will not let me. Here we go. Yeah. So on the right here is called a triglyceride. So what does hopefully some people have read this already. What does the glyceride refer to? Why do we call it a triglyceride? I think we can see why it's called tri, because there's 1, 2, 3 fatty acids there. But what are they connected to? So Fa stands for fatty acid in biochemistry. And to make an ester, we need an acid. And what else do we need? What's the other molecule that makes an ester? It's an acid plus something.
Alcohol?
An alcohol, that's right. And so where's the alcohol in this molecule? It's a very special kind.
Is it glycerin?
It is. Excellent. Yeah, it's called glycerol. That is why, or glycerin, depending on, it's used interchangeably. Glycerol, all stands for alcohol. And it's a special kind of alcohol because it's got 3 hydroxyl groups on it. So it looks like this. So it's 1, 2, 3. And there's an alcohol group on every single carbon. So basically it is a propanol, but it's a tripropanol. So 1, 2, 3 tripropanol. And so each one of these groups forms an ester bond with a fatty acid. So there's 1 there, there's 1 there, and there's 1 there. So that's why we call it a triglyceride. So there's 3 fatty acids, that's the tri, and the glyceride comes from the glycerol part. So this is, we see triglycerides a lot. You probably, most of you aren't old enough to have your blood taken. That's one of the things they test you when you're old and feeble. You know, they test you for your cholesterol level, your triglyceride level. So if you have a high level of triglycerides in your blood, it means you have a lot of fat in your blood. And so you should have some triglycerides in your blood, but not too many. And then they check you for low density lipoproteins, or LDLs, and then high density lipoproteins, or HDLs. HDLs are good because they remove cholesterol from your body, and LDLs are bad because they put cholesterol back in. So this is one of the typical ways that that fats, this is a fat basically right here. It's a triglyceride with 3 fatty acids attached to it. So soap was basically discovered by taking animal fat and treating it with a strong base. And so you take animal fat, and this is a fat right here, and you treat it with a strong base. So potash was considered, was one of them. Basically, it was the residue, like ashes, residue from a fire. And that has a large quantity of sodium and potassium hydroxide in it. So if you add hydroxide to a fat, it breaks these ester bonds. And when you break the ester bonds, you're left with a fatty acid that now, instead of having, will have a double bond and a negatively charged carbon. So what you've got now is a long chain fatty acid with a negative charge once you've broken all these bonds. So what does that give you? Well, that, as we learned this morning, when you have these really long chains, that makes a micelle. So here's the reaction again. So this is a fat in coconut oil. So coconut oil is pretty much, anyone used coconut oil in cooking? Does anyone, yes? Or even on your hair? I don't know, like some people put coconut oil on their hair. Yeah, so at room temperature, is coconut oil fat? Is it a liquid or a solid?
Depends the temperature. If it's warmer, it's liquid.
Right, but at room, like it's slightly cooler than room temperature.
Pacifica is probably solid.
Right,
Solid is
exactly.
liquid.
Yeah, because you get these really long fatty acids in there. So it is a 18 carbon fatty acids. That's a long stretch. And they're all single bonds. So they're able to stack right on top of each other. And so there's a lot of London dispersion force going on there. And so at room temperature, it's pretty much a solid. You heat it up just a little bit and it starts to turn into a liquid. But when we add hydroxide to it, you see it takes 1 mole of this triglyceride and 3 moles of hydroxide, 1 mole to break this bond, 1 to break that one, 1 to break that one. And what you release is glycerol is 1, and the other product is the fatty acid with the negative charge. And that's what we call a soap. So to make a soap, you need a really long fatty acid chain so that you get a hydrophobic interior. So what it makes that micelle we talked about, you get a hydrophobic interior. If this carbon chain is too small, then it just dissolves in water. So this wouldn't work if we had just like 3 or 4 carbons, because then it would be fairly soluble in water and we get a very poor micelle. If you get really, really long carbon chains, you get a nice big hydrophobic middle. So you can push this reaction forward by adding high concentrations of sodium hydroxide and heat. So in a commercial soap making facility, they do what's called the hot reaction, where they have extremely concentrated sodium hydroxide, like 10 to 12 molar, something that we're not going to be dealing with because that's really, really dangerous, and very high temperatures. And so this reaction goes really, really fast. What we're going to be doing is the cold reaction. So at room temperature and with much lower concentrations of sodium hydroxide. So why is the reaction that we're going to be doing going to be much slower than the reaction done in a soap factory? There's 2 basic reasons. Our reaction is going to take like 3 days to complete. We'll just start it today, but it won't be finished till like Friday. Why is our reaction going to take so much longer?
Is it because we're not adding heat?
We're not adding heat. What typically happens to the rate of a reaction when you increase the temperature?
There's a higher reaction rate.
Almost always, especially if it's an endothermic reaction. And this is an endothermic reaction. The more heat you put in, the faster it goes. And like the reaction we did last week, we noticed that when we increased the temperature, the catalase reaction went faster. And that's typical for most. So that's one reason. So one reason is the temperature is lower. What's the other reason going to be? Remember I said there was 2 things that, for the hot reaction that the soap factory does. One of them was heat. What was the other one?
Was it the sodium, like sodium hydroxide concentration?
Exactly.
Lower?
We're going to be using a much lower sodium hydroxide concentration. So our sodium hydroxide concentration is going to be about 1 molar rather than 12 molar. And if you decrease the concentration of the reactants in a reaction, what typically happens to the reaction rate? If I have a reaction between A and B and they make C, and then I lower the concentration of A or B, what's going to happen to the rate of reaction making C? Is it going to speed up or is it going to slow down?
Slow down.
Slow
It's going to
down.
slow down, right? If you reduce the concentration of either of these reactants, so we have two, we've got the fat, we got the fat on the left, and we've got sodium hydroxide. You reduce the concentration of either one of those, less chance they run into each other, less chance they undergo a reaction. So the temperature is going to be lower, the concentration of hydroxide is going to be lower. So our rate of reaction is going to be much, much slower. That's why it's going to take like 3 days for the reaction to complete itself. Okay. So we're going to be doing 2 activities today. One, we're just going to start activity 1. We're going to start making our soap from vegetable oil. So it's a liquid at room temperature, so we don't have to melt it. That's one of the reasons why soap making facilities generally use the hot reaction, because they're using fat. They're using solid at room temperature, so they need the high heat. One of the reasons the high heat works well is that it melts it into a liquid. We'll already have a liquid. And so we'll be using vegetable oil and 1 molar sodium hydroxide. So it'll be less solid than your typical bar soap, but it'll still be solid. It'll be a little mushy. So we're going to mix those 2 together and try and get them, mix them as well as possible. And then after 3 days, you'll basically what'll happen is that you will have a in the middle between a soap layer will form. You'll see like a sort of like a solid white sort of soap layer with sodium hydroxide on the bottom of it, because it should be slightly less dense. And what we'll do is we'll add some sodium chloride solution to help rinse all of the sodium hydroxide away. And because basically you don't want to have concentrated sodium hydroxide in your soap. You could imagine washing your face with concentrated sodium hydroxide. Not fun. So you'll be doing that on Friday or Saturday, whenever you get to it. So that's what we'll start today. The second one that we will do a bit today is go over what reactions you're going to be doing with the soap. We're going to check its pH to see whether it's been rinsed properly. If it hasn't been rinsed properly, the pH should be very high. Typically, pH for soap should be somewhere between like 7 and 8, 7 and 9. Anything more than 9, it really starts to burn your skin and cause irritation. Oh, there it is, 7 and 9 right there. So we're going to do that. We're also going to check to see whether or not we can make micelles. Basically, can we make bubbles with our soap? So that's something I talked a little bit about this morning, talking about hard water and soft water. So this is what the micelle, if you remember, looks like. And on the outside, if we just have sodium ions in solution, they will bond with the negative charges of your fatty acids. And so then basically you will have neutralized charge, and they'll just float around, interact with each other, and not really bother anybody. But the minute you have hard water with either magnesium or calcium is really bad. If you have calcium, what happens is that you basically force two of these fatty acids to bind to the calcium, and you push them really, really close to each other. And when you push these things really, really close to each other, basically you pull them out of the micelle. And what happens a lot of time is it will precipitate, because you'll have this long chain that now is being forced to go into the water. It doesn't like being in the water. It doesn't make enough interactions with the water. So what it typically will do is just fold up on itself, and it'll just crash out of solution. And so has anyone tried to clean their bathtub or their sink of soap scum? If you've heard of soap scum, hopefully. Yeah, that is because you get these big lumps of soap that are interacting with these divalent cations. And so they're not soluble in water. They don't form bubbles. They just sort of clump together in a solid. So they're really, really hard. They're really, really hard to clean, because basically you're trying to clean something that's already soap. So what do you clean soap with? So it's hard to dissolve them and get them back into solution because of the presence of these divalent cations. So what we'll do is we'll just take a little bit of household soap, and you can use liquid soap, or you can use some hand soap, solid soap, whatever. And we'll see what the difference is between whether they can form micelles in the presence of oil. We're going to put a little of that vegetable oil that comes with the kit. We're going to take a little bit of that vegetable oil and see if our soap can form micelles around it. And then we're going to add a little bit of divalent cations. It comes basically just a mixture of, it says hard water mixture. It basically has magnesium, calcium, and iron in it. And then see, can it still make micelles to trap the oil in? And you'll see, I think you should see a fairly dramatic difference. So what are we going to need this afternoon? So we're going to need 1 molar, oops, we're going to need the 1 molar sodium hydroxide. So I think we have a couple of different, it either comes in this kit or in this particular bag, or I think there's a lot of other reactions. I think I've got like 2 or 3 of these now, but we're going to need the 1 molar sodium hydroxide. Comes with some vegetable oil. Look for a screw cap. So it's going to be a glass vial with a black screw cap on it. That's what we're actually going to make the soap in. And those come in these bubble wrapped containers. If you haven't been able to find it, they come in the bubble wrapped containers. So these glass test tubes or plastic test tubes, I don't think it really matters which one. There should be a glass stirring rod in there. My glass stirring rod got broken, so I think I'm just going to use a pipette to stir things with. Like I said, there's a bag of hard water mix. It's going to dump the whole thing. Unfortunately, one of my dogs got into it and chewed a hole in it. So I don't know actually how much hard water mix I have left, but I'll try and make do. These other things you're going to need later. So later on, you're going to be rinsing your soap that you've made with the saturated sodium chloride mixture. What's a saturated sodium chloride solution? What does that mean? What is that? We did saturated solutions a little while ago. If a solution is saturated, what does that mean? Man, we've forgotten what saturated means. If I add more salt, if I add more sodium chloride to a saturated solution, is it going to dissolve?
No, it's gonna precipitate.
Right. It means we've dissolved all the sodium chloride in. We can't possibly dissolve anymore. Basically, every single water molecule in that solution is interacting with a salt. So there ain't no more room for any more salt to interact with water. So if I throw any more salt in, it's just going to settle to the bottom. So that has maximum saturation. So we're going to need a couple graduated cylinders. I have not been able to find a 100 ml beaker. Does anybody have a 100 ml beaker in their kit? I have a 250 ml beaker. I'm not sure such a thing exists. So I was just going to use one of the plastic cups. Because I don't think we have a 100 ml beaker. I'm not sure. Maybe I just don't have one. That's certainly possible. And then a scale, weigh boat, and plastic spoon. So yeah, check on that when we break to get all our stuff together. So first, we'll start with the soap preparation. This will only take a second. So we're going to take that vial with the screw cap. That's called a dram vial. It has the black screw top on top of it. So we want about 2 grams of vegetable oil in there. So we just take the plastic pipette and then pull up, then squirt into the dram vial on top of the balance after you've tared it. So about 2 grams. Doesn't have to be exactly 2 grams, about 2 grams. Then we're going to want 2 mils, and again, approximately 2 mils, 1.9, 2.1, that's fine, of our 1 molar sodium hydroxide. And then pour that in with it, screw the cap on good and tight. And then you'll see that there's a layer with one thing floating on top of the other thing. Who's going to be floating? Is it going to be the oil or the sodium hydroxide? Which one is going to be on top?
Wouldn't it be the sodium hydroxide?
Actually, it's the oil.
Oh, what?
Yeah. The oil, because if you pour oil and water together, which one goes to the top? If you make salad dressing yourself, generally the oil goes to the top. It's less dense. It's a much bigger molecule, but it doesn't pack together nearly as tightly as water does. So generally the oil, I'm pretty sure the oil in this instance is going to be on the top. So what we're going to do is just going to shake it and try and form a suspension. We want to get as much interaction between the oil and the sodium hydroxide as we possibly can. And then then an emulsion will form, like the suspension with like really small molecules with really small bubbles, it's called an emulsion. And then we're just going to, it'll separate, and then we want to shake it up again. And then we'll just put it away in a dark place, secure, away from children and pets and everything else for at least 72 hours. And then what'll happen is that we'll see the sort of soap settle in the middle. And it should be, like I said, it'll be solid, but it won't be like super hard. And it should be white, or maybe a little beige in color. So we'll just get that reaction started today. So after 3 days, that forms at the interface, and then you're going to filter it. So fold up the filter paper with your funnel. Take 2 mils of the 25% sodium chloride solution. I guess it isn't saturated, it's 25% saturated. Shake it up, put it in the solution, shake. What you basically want to do is separate the hydroxide and the soap. And the sodium chloride will help do that. Because basically what you're doing is you're replacing the hydroxide ions with chloride ions. And so hydroxide ions, bad. Chloride ions, not so bad. And then you'll filter it and wash it a couple times. So once you have your soap, we're going to take about 0.5 gram of it and put it into either our beaker, if you have it, or one of the plastic cups. Add 50 mils of water, pure water, either filtered water. If you have to use tap water, I think now's the time where you really want to use purified water, because we want the water to be as soft or as low on divalent cations as possible. So then mix that up, take 5 mils of that solution and put it in our test tubes. Then we're going to check the pH. So either with a glass stirring rod, we should have pH paper, should be in this particular bag as well for this particular experiment. There should be some, like at least 6 to 8 pieces of filter paper. So basically what you're going to do is just take a drop from the soap solution, touch it to the filter paper, then compare it to see what color it is. So the lighter the color, the lower the pH, the darker the color, the higher the pH. And you want to use gloves for this, because there will be sodium hydroxide around. So we will be using gloves today. Here. So take a picture of the foam layer that you make. Second thing, we add 2 drops of the vegetable oil, and that same thing is what we want to do is we want to see, can the soap micelles form around the vegetable oil? So what should happen, you drop the vegetable oil in, you'll see it separate. When you shake it up, that basically should just disappear. You shouldn't be able to see the vegetable oil anymore. What should happen is that it should just go into the micelles, and then basically it'll be gone. It'll be captured inside the bubbles. So take a picture of that layer as well. Then we're going to make the hard water. So this afternoon, we're just going to be doing this with a household soap sample. So you're going to find either some liquid soap or some hard soap, something that will look something soapy. And we're going to be using 1 gram of that rather than 0.5 gram. So we'll take the hard water packet, pour it into the 50 mil graduated cylinder, add water, shake that up, and then put that also into the beaker that has the water plus the soap you had before. So you should have had like 1 gram of soap, 50 mils of water, and now plus another 50 mils of hard water. Take 20 drops of this and put it into test tube numero dos. And then we're just going to do exactly the same things we did for the soft water. We'll just shake it up, see if it makes what kind of layer it makes. Take a picture of that. Drop 2 drops of vegetable oil in there. See if it can make the vegetable oils go into the micelle. Okay, and that's basically it. So it's not going to be a really long lab today. We're going to get something started, and then we will work on this part of the of the report. So we'll have our household sample, and then 3 days we'll compare it to our soap we've made ourselves. So you're going to want to hold on. Ooh, actually, no. Because you're going to be making your hard water, you're not going to be able to do that. Interesting. Because yeah, you only have one hard water mixture packet. I don't know how you're supposed to do both of these. So, but I guess what we're going to have to do is take the hard water mixture packet, put it in the 50 mil graduated cylinder, and then take 25 mils of that plus 25 mils of our soap mixture and add those together. Save the other 25 mils of the hard water mixture for your prepared soap sample. So yeah, let's just realize that now. So I'll go over that again when we get all of our stuff together, because I want to be able to finish this part of the reaction of the experiment today, and then you'll be able to do the soap sample with the stuff you've made. All right, sorry that was so confusing at the end. So any questions before we go and get all of our stuff together? Was anyone able to find a 100 ml beaker?
No, I wasn't.
Yeah, I think so. I think we're just going to have to use a plastic cup. So that'll definitely hold 100 mils. So this might have been, these instructions may have been for a kit that had a 100 ml beaker in it, but we only have the big one. So you can use the big one if you want. That's fine. So either way, either you use the 250 ml beaker or you use a plastic cup. Either way, they'll both easily hold 100 mils. Okay, so if there are no questions, a lot of different things to grab and put together. So you're going to want gloves as well as your goggles, since we're going to be dealing with concentrated sodium hydroxide today. Not super concentrated, but concentrated enough. And we're going to be, putting our thumb over it and shaking it and all that sort of stuff. So yeah, gloves and goggles and all your stuff. So let's get back together in, let's say, 15 minutes. Long enough for everyone to get all their stuff together? All right, cool. So at 2 to 3, I will see you, and we will start making soap. All right. Let me pause this and I'll see you guys in a minute. So first part is actually we're going to start making our soap. So here's the vial with the screw cap on it. And where is my, oop, I put my balance over here. Remember, we're going to want about 2 grams. So it's got grams. Put the vial on. Vial weighs about 8.4 grams. I will tare it. Here's my vegetable oil. It comes with. And then get about 2 grams. It's pretty close. 1.94, I'd say that's close enough. And then 1 molar sodium hydroxide. We're going to want about 2 mils. And that's about 2 mils. If it's a little more, that's fine. It's basically going to be salting away the sodium hydroxide anyway. And pour that in. So you see the oil will be a little bit darker than the sodium hydroxide. So we'll be able to see which layer floats to the top. You can see pretty clearly that the oil is on the top and the water, the sodium hydroxide solution is on the bottom. So seal that pretty tightly and give it a really, really good shake. And if you hold it in your hand, actually notice that it's, what temperature does it feel like? Is it warmer or cooler? Is it cold to the touch or is it a little warm to the touch? What have people noticed? No one's noticed anything. Is the temperature changed? Jessica, have you noticed?
It feels a little colder, I think.
Yeah. So what does
Okay.
that tell you? What kind of reaction is this? If it feels cold to the touch, is heat going into the reaction or is heat coming out? Which direction is the heat going? If it's cold, is it going in or is it coming out? Someone help her out. Ryan, what do you think? The heat going in or is it coming out?
Isn't the heat coming out if it's giving off warmth?
If it's good, yeah, but is yours getting warm or is it feeling cooler?
Mine feels room temp. I mean, I'm
Oh, it
not
hasn't changed.
yeah.
Yeah, it's not a dramatic difference, but I do think it's a little bit cooler. So that means the heat's going into the reaction. So does that make it endothermic or exothermic?
Endothermic.
Endo.
isn't it?
That's right. It's an endothermic reaction. So we're just going to let that sit. You can see it's starting to separate already. So let that sit for about 10 minutes or so.
Yeah, I actually noticed that it does feel slight cooler.
Well, yeah, now that we've put that suggestion in your mind. Right, I'm going to start making my solution of house soap. Oops. So since I don't have a 100 ml beaker, I'm just going to use one of these plastic cups to make my solution. So I am going to pick, see, I have a number of different soaps I could try. I think I'm going to try liquid hand soap. Yeah, so I've got this hand soap from Trader Joe's. It smells wonderful. Smells like grapefruit. So I'm going to want about a gram of that. Man, this stuff is thick. There we go. And 50 mils of water. Got my purified water here. And then get my spoon to mix it up. Yes, you want to mix it up. You don't want to like shake it too hard so that it's just, you get nothing but bubbles. I mean, you do want the soap to go into solution. And you can try dish soap. You can if you've got some like natural soap, that might be the best. If you've got some like, you know, soap you bought at a farmer's market or something, it's kind of soft, that would work really well. The way they make soap sort of is not terribly different from the way you're going to be making it. Okay, so that looks like it's pretty much mixed. So first thing I want to check is the pH. It's like I said, my glass stirring rod was broken, so very sad. So here's the pH strips we're going to be using. And it comes with a nice little colored guide to let you know what we should be looking for. It won't come out of the bag. There we go. Oh, so you got a lot more than 10. Man, you got a ton of these. So you can just go around the house testing pHs of different things. Yeah, try like milk and orange juice and stuff like that. It's a lot of fun. So I'm just going to take a little drop. And then just let it, so wet it and then just let it sit. The color will take a while to develop. So you can see that with my soap, at least, the color really hasn't changed at all. Maybe it's even a tad lighter. And that could be because the soap I used had grapefruit in it. Grapefruit is acidic. So it looks like if I hold it up, probably about there. Looks to be about the match. So I'd say this is about probably between pH 6 and pH 7. So it's a little more acidic than I would expect. Most soaps are more alkaline. But yeah, this looks right between 6 and 7. Yours will be, the homemade stuff will be, should be a lot more basic than that. So back to our, so you see this thing is starting to separate already, although it's not nearly as separated as we first put it in there. So what we need to do is shake that up again. But you can already see that in between the two layers, the soap is actually starting to form or starting to get, it's not really a solid yet, but there is a reaction starting to occur. Because you remember before the oil was clear, now it's not. So we're forming a new substance in there. So give it another good shake. Yeah, like wine might watch at the same time. There we go. And you can even shake it again at the end but yeah, definitely starting to see a reaction take place because the color's changing slightly. And we're starting to get bubbles where we didn't really see bubbles before. So we've made a tiny bit of soap already, but this is a fairly slow reaction. All right. So back to my soap solution. So I've got a test tube. You can use either, I think you can use either the plastic test tube or the glass test tube. It really shouldn't matter. And take 5 mils out of there. Yeah, so pour it relatively gently so you don't make too many bubbles before you want. All right, 5 mils. So there's 5 mils in my test tube. So here's where you want to make your first, take your first picture. So you put your gloved thumb over it, give it a good shake. And you can see, I mean, yeah, it kind of makes a buttload of bubbles. Not a huge surprise there. So basically take a picture of that so you'll have something to compare your homemade soap to. So you can see this has made it just an insane amount of bubbles, which we would expect. So here's our vegetable oil. So we're going to put a little 2 drops of vegetable oil in there. And see if the vegetable oil disappears. Yeah, and quite clearly it does. I do not see any vegetable oil in there. And we could probably add a few more. And then you want to take a picture of that one as well. Now you can see it doesn't really look any different. I could probably put quite a bit of vegetable oil in here. There we go. So now you can see I've got you can see the vegetable oil clearly on the top there. I've added like way too much. But let's see if it will disappear when we shake it. And it's gone. Yeah, you don't see the oil. There's no oil. There's no separation there. That's what soap's supposed to do. So, oh, let me see a little bit there. You can sort of see 3 layers there, if you notice. So there's sort of an aqueous layer at the bottom, and then a little bit of oil there, and then the bubbles. But yeah, it took quite a while. So with the second tube, I'm going to try the hard water. Because yeah, this will be tricky because you can see it's sort of got dog tooth marks in it. So I really don't know how much I have in here. So it says right on here, if you read the ingredients, it has sodium bicarbonate, calcium chloride, and magnesium sulfate. So it's calcium and magnesium are the divalent cations in here. There's no iron. Oh, looks like I got I got some solids in here. Hopefully it's enough. Let's pour that directly into the 50 ml. So you guys are probably going to want to add the 50 to it, shake it up, make sure it's all dissolved, and then take 25 mils of it and I don't know, put it in something. I'm not sure what would be a good thing to put it in. Maybe one of those small cups, the medicine cups, might be good. Yeah, probably put it in one of these small medicine cups and then put a cover over it with like some tin foil or something. And then save 25 mils of it for your second experiment for your homemade soap. So this you're going to want to cover with your gloved hand too, or you just take some saran, put it over the top. I think I'll do that. Yes, put saran wrap over the top of it so make less of a mess. Make sure you've got it good and tight. Yeah, you can see there's lots of floaty bits in here, so it might take a minute to get this all dissolved. And if you noticed on the ingredients that both the calcium chloride and the magnesium sulfate were both hydrates, which we did an experiment with earlier. And because they're hydrates, hopefully they will dissolve a lot faster. The anhydrous salts are really hard to dissolve. But if they already have water in them, they dissolve a lot faster. No, I still got big. No, it's taken a while. Oh, man. Still not dissolving. You guys having a hard time getting this stuff to dissolve? I figured this would dissolve a lot faster. Yeah, this is cold too. Maybe if we heated it up a little bit. Nope. Still got floaty bits. Anyone able to get theirs into solution yet? Or is it still looking cloudy?
I'm having the same problem.
Yeah. Yeah, maybe we should like microwave it for, I don't know, 10 seconds or something. Oh, man. Yeah, it's taking forever. I'm gonna try that. Just like 10 seconds. Not too long. I don't want to melt this thing. This feels slightly warmer to the touch. Luckily, it just fit. I mean, it just barely fit. Oh, seems to be dissolving a little better now. And still. Yeah, I'm still getting a bunch of solids at the bottom of this. I can wonder if yeah, it doesn't say anything in the instructions about how long it's supposed to take to go into solution. Supposedly you gently stir it. Yeah, I don't think so. All right. So you're going to want to take like half of this and pour it into the medicine cup and then put it away for a rainy day. I'm going to be using all 50 mils of my solution. So I'm just going to dump the whole 50. What you're going to want to do is take half of this, 25 mils, and mix it with 25 mils of this, okay? And stir this up. right, so take 5 mils of this and put it in my second test tube. So now this is my commercial soap hard water. And give it a shake. So I'm still getting bubbles, but not nearly as much. This is with soft water and like at least a milliliter or more of oil in it, and I've still got a lot more bubbles than I've got over here. I still get bubbles, just not as many. I also get some strange color in the top too. You see it's a little dark. I don't know what that's from. There's a little dark color on the top as well. So then take a picture of that. Also put your vegetable oil in. And give that a shake. Let it separate. Oh, and if you look really closely, so this is all like white bubbles up here. And then down here is soap solution, but you can see in between, there's a layer of oil. So this time the oil did not go into the micelles nearly as well. I mean, some must have, but you can see the oil layer here. Whereas before, with the soft water, there wasn't. This took like about 2 mils of oil for you to finally see a layer of it. This was only 3 drops. Yeah, so the hard water definitely makes a difference. So that's basically it. That's like, so you take so you're going to take a picture of just the soap by itself, shaken, to see how much bubbles you get. 3 drops of oil shaken to see if you get does all of the oil get distributed into the micelles. Take the pH of the soap solution. And then with your homemade soap, the same thing. Bubbles by itself. What does the bubble layer look like with 3 drops of oil in it, and what's the pH? And so we want a picture of the layer without oil, layer with oil, layer with oil and hard water. I think that's all in the report template. I think there's 6 pictures in total. Not too many long essay questions in this one. And then you've got all this oil and soap to clean up, which is terribly fun. Yeah, I'm really surprised the pH of my soap is so low. I'm going to test that one more time. Oh, there we go. Oh, of course, this is with the calcium in it. Yeah, note, look what happens to the pH with the calcium and the magnesium in it. It drops or it increases. It went from about 6.5 to about 8. Oh, right, because it's got sodium bicarbonate in it. Oh, that makes sense. All right, so anybody have any questions about how to proceed from here? You can give your homemade stuff another good shake before you leave it. Because you want to have, and I'll take a picture of this as well and send it out in an announcement. Just I might even have my soap from last term. I'll check downstairs. Yeah, like I said, so just find some place where that won't be disturbed, and you should see a nice sort of big lump in the middle. If you have any questions on how to proceed from there, let me know. I'll try and help you out.
Professor,
See, Jennifer, what's up?
I'm trying to test the pH after I did the soapy solution.
So yeah, test it before you add the hard
Is it-
water additive.
Oh yeah.
Yeah.
Yeah, I just use a water and the soap,
Yep.
and
What kind of soap did you use?
I think it changed style. Let me see if I can turn on my video.
All right.
Yeah.
Oh, okay.
It's right here. There's not much change to my paper.
Yeah, that's to be expected, because I think what most
Okay.
commercial soaps are going, they don't want people to burn their hands, right? So what they're going to do is generally they're going to make sure that the pH is almost neutral. So it should be pretty much the same color. Because yeah, I mean,
Okay.
yeah, mine was
and-
like pH 6.5. So I was actually surprised with how low that was. So so the color of yours was, what was it closest to, 6 or 7?
6.
Anybody
I
else?
think it's 6.
What other, did anyone get like a more basic pH with the soap they used? What were the different soaps people tried? What did you try, Taylor?
So mine was Suave coconut water, and I also got 6.
Huh. So that's like a pump soap kind of stuff? Is that shampoo?
No, it's hand soap.
Oh, okay. What about you, Ryan? What kind of soap did you try?
I used the Dove soap bar.
Oh, bar. Oh, cool. So what pH did you get?
I got a pH of 6 as well.
Oh man, so everyone, so it seems like all the commercial stuff has been treated to get it to a neutral pH. That makes sense. That's why I kind of figured if someone had like sort of, actually I have we do have some natural. I should have tried that. That's what I'm going to do. I'm going to test that. I'm going to take some, because we've got some like, soap we bought at a farmer's market. And I want to see if that has more of a alkali nature to it. Although that's probably treated to bring it to more neutral pH as well. But I will test that. So everyone's got like neutral to slightly acidic pH so far. Dee Dee, you got the same thing? Huh, interesting. Okay. All right, so you can see it's fairly straightforward.
Are we supposed to?
Oh, go ahead.
Oh, are we supposed to save this water? The soap water?
No, when you're
we have
done,
this?
no, just, yeah, add,
Oh.
like, take 25 mils of that, add 25 mils of the hard water addition, then mix that up, you can throw the rest away.
Okay.
Yeah, you only need like 25 mils of it. And then once you're done with that, you can just toss it all out. But yeah, you're gonna want to save half of your hard water mix for your homemade stuff.
Professor?
Oh, question?
Yes.
Yes.
Uh,
Oh, Jessica,
so-
yeah.
what is supposed to be the difference between the hard water and the purified water with the soap? Because I got the foam, it's the same.
Exactly the same.
Yeah, if you compare,
Because one's had oil added to it, right?
yeah, this one already has the oil added to it.
Right. So yes, you really can't compare them till you add the oil to the other one as well.
Oh, okay,
Yeah.
but still.
Yeah. Yeah. I'm surprised like how much.
And like,
I would-
and it didn't mix much because you can see it like at the bottom of the cylinder.
Yeah, I think
Yeah.
that may be one problem is that this stuff isn't terribly, I don't think all of it went into solution. So that could be why the water's not as hard as we would like it,
Okay.
Yeah, I see the same thing. Yeah, my mixture has solid chunks on the bottom. So it could be that just this isn't as hard as it could be. But maybe they didn't, it isn't the hydrate, maybe it's the anhydrous salt, and that just doesn't go into solution. But hey, that's why it's called an experiment, right? But I definitely saw a difference with the oil. Even if I did see slightly less bubbles with the hard water, but with the oil it was the big difference because all of the oil went into the micelles. With the soft water, with the hard water, even three drops, I could see it. It's separated. I still have that oil. Just with 3 drops, I still have it separated. So
we should add the 3 drops to the hard water too?
yes.
Okay.
Oh, dear. There's a fly in the house and the dogs desperately want to eat it. All right. Any other questions? Well, how you doing?
Okay, so the pH, I think I got pH of 8.
Ooh, what was your soap?
It's soft soap.
Interesting. Okay.
Yeah. At first it's 7, like 6.57, and then after a few minutes it turned 8.
Yeah, the 8 is pretty different. Yeah, the difference between 6 and 8 is really, really clear. So,
It's green.
yep. Yep. 7 is kind of like an olive color, and then yeah, 8 is definitely green.
Like
Oh, cool. Okay. Yeah, so yeah, I think it's interesting. All different soaps, different pHs. Yeah, I would like try dish soap too. I'm kind of curious to see, because with dish soap, they probably aren't quite as worried about the pH, or maybe not. I'm not sure. because we don't use nearly as much of it when we're washing. When you're washing your hands, you use a lot of soap. But dish soap is a lot more concentrated, so. Yeah, so I'll check both dish soap and natural soap and get back to you. Oh, how you feeling, Dee Dee? You feeling better?
I feel fine now.
Excellent,
Thanks.
excellent. Good to hear. Full recovery. All right, everybody. Send me a group meeting tomorrow at group meeting. Still can't get it a lab mode. Office hours tomorrow at noon. And if you have any other questions, let me know, okay? All right, everyone, gotta walk these doggies. I'll talk to you soon.
Thank you.
All right, bye, everyone.
A good one.
You too.